Hi everyone. Today we're going to continue chapter 18, but we're just going to work on some of the worksheet problems. So these were a couple of problems that I thought were good practice for some of this material, but I didn't really include them within the lecture just because they're kind of their own thing. So um, we're just going to use what we've learned so far and apply that to these problems. So let's start with worksheet problem 8. And again, if you want to try these on your own first, I highly recommend it, and then you can follow along and see if you did the same thing I did. So in photosynthesis, plants form glucose, which has the molecular formula C6H12O6. And oxygen is also formed from carbon dioxide and water. So write a balanced equation for photosynthesis and calculate the enthalpy change of the reaction, the entropy change, and Gibbs free energy at 25 degrees Celsius. Is photosynthesis spontaneous? So let's start by writing out that equation, so the balanced equation. So we're told that carbon dioxide and water are reacting to form glucose and oxygen. So C6H12O6 and O2. Now I am going to include the states here because that will be important when we're calculating enthalpy and entropy, etc. Because some of those values do change based on the state. So CO2 is a gas, and then H2O will be a liquid because if we're thinking about a plant, it's drawing up water from either the soil or maybe moisture that condenses onto it. So that's a liquid, and then it's also drawing in carbon dioxide gas from the atmosphere around it. And then glucose, we're going to call this a solid, and oxygen is a gas. Okay, so now we need to balance this reaction. So I'm going to make a little reactants versus products table because that usually helps me keep track. So let's start with carbon. On the left we have 1 carbon. On the right we have 6. And then let's go to hydrogen next. I'm skipping oxygen for now because it's split up between 2 reactants and 2 products, so that's going to make it hard to balance initially. So hydrogen, we have 2 on the left and 12 on the right. And then oxygen, let's see, on the left we have 2 oxygens in carbon dioxide and 1 in water, so that's a total of 3. And then on the right-hand side, we have 6 oxygens from glucose and 2 from oxygen, so that's 8. And again, that's going to be hard to balance, 3 and 8. So we'll balance that last. Okay, so let's start with carbon. We need 6 carbons on each side. So on the left, let's multiply CO2 by 6. And then if we jump to hydrogen, we need 12 on each side. So let's multiply H2O by 6. And now let's recount our oxygens because the number of oxygens will have changed on the left-hand side. So we have 6 times 2 from CO2 plus 6 times 1 from H2O. So 6 times 2 is 12, plus 6 is 18. Okay, and then on the right-hand side, we have 6 plus 2 oxygens, but we need that to equal 18. So maybe let's try to multiply the oxygen O2 that's by itself by some factor in order to get to 18. So let's see, let's use this algebraic equation we wrote out and solve for x. So 2x is equal to 12, and then x is equal to 6. Okay, so that means if we multiply O2 by 6, that should give us a total of 18 oxygens on the right-hand side. But let's double check. So we have 6 oxygens in glucose plus 6 times 2 oxygens in O2 there. So we've got 6 plus 12, which is 18. All right, so that works out. So our ratios now are 6 to 6 to 1 to 6. Perfect. Okay, so now the next step, let's calculate delta H and delta S, because those will help us determine delta G. All right, so I'm going to rewrite the equation that we just balanced so that we can kind of keep track of what we're actually doing here. Okay, so if we're going to calculate delta H and delta S, we should probably look up the enthalpies of formation for each of the reactants and products, because we're going to want to use the equation where delta H of reaction is equal to the sum of the moles of each reactant and product multiplied by their respective enthalpy of formation. Oh, and then we're going to subtract the same thing but for the reactants. Okay, and then we'll do the same with delta S. So we'll also need the molar entropies here. Okay, so let's make a little table and we'll look up the values for the reactants and products for each of these. So let's see, we'll put molecule in the first column, and then we'll put delta H of formation, which is in kilojoules per mole, in the next column, and then we'll put the molar entropies in the last column. And its unit is joules per mole Kelvin. All right, so let's start with Actually, let's start with the products because that's the order we're going to be using them in. So we'll start with glucose. And it's a solid. So if we look in the back of our textbook, there's a bunch of enthalpies of formation and standard entropies listed for many different molecules. And let's see, for glucose, the enthalpy of formation is negative 1,273.3, and its entropy value is 212.1. And then for oxygen, what's really nice is that its enthalpy of formation is 0 because it's a pure element, but it does have a positive entropy value. So let's look that up. So for oxygen, that is 205.2. All right, and now we'll go to the reactants. So CO2, gas, has an enthalpy of formation equal to negative 393.5. And for water, or oh, sorry, for entropy, it's looking at the wrong thing. CO2's entropy value is 213.8. All right, now for water. And we're looking at the liquid state. So its enthalpy value is negative 285.8, and its entropy value is 70. Okay, so now we have everything we need to calculate the enthalpy of the reaction and the entropy of the reaction. All right, so let's start with enthalpy. So again, we're going to add up all of the enthalpies of formation for the products and then subtract the enthalpies of formation for the reactants. All right, so we also want to take into account any stoichiometry or ratios. So there's only 1 mole of glucose, and we're going to multiply that by the enthalpy of formation of glucose, which was 1,000 or negative 1,273.3 kilojoules per mole. And then we're going to add the enthalpy of formation for oxygen. So there were 6 moles of oxygen, but it doesn't really matter because the enthalpy of formation is 0. So that will just all be 0 there. All right, and then we're going to subtract the reactants. So carbon dioxide, there are 6 moles present, and its enthalpy of formation is negative 393.5 kilojoules per mole. And then we want to add the other reactant, which was water, and there are 6 moles of water, and its enthalpy of formation is negative 285.8. All right. Okay, so we're going to add or subtract everything together, and at the very end, we should get positive 2,802.5 kilojoules. Okay, so if the enthalpy for this reaction is positive, is this an endothermic or exothermic reaction? It's endothermic. Okay, so we can probably start to make some predictions about whether this is spontaneous or not. So this could be temperature dependent, but let's see. So we'll calculate delta S next. So again, starting with products, we have 1 mole of glucose, and its entropy value was 212.1 joules per mole Kelvin. And then oxygen, we have 6 moles, and its entropy value is 205.2 joules per mole Kelvin. All right, and then we're going to subtract the reactants. So again, we have 6 moles of CO2, and its entropy value is, looked at the wrong value there, 213.8 joules per mole Kelvin. And we have 6 moles of water, and its entropy value is 70. Okay. So now we can plug that into our calculators, add and subtract everything we need to, and we'll end up with a value of negative 259.5 joules per Kelvin. Okay, so this value of entropy for the reaction is negative. So is entropy increasing or is it decreasing? So it is decreasing. And that makes sense because if we go back and look at our reaction equation, up here, initially we have 12 moles of reactants and only 7 moles of products. So we're going from a lot of moles to fewer moles. So that means entropy is decreasing. Now, if this is an endothermic process and entropy is decreasing, we can probably start to make some predictions about whether this is a spontaneous reaction or a non-spontaneous reaction. However, there's one more thing we need to do. We need to calculate delta G, the Gibbs free energy. All right, so let's calculate delta G. So remember, delta G for a reaction is equal to delta H of the reaction minus temperature times delta S of the reaction. So now we can just plug in the values that we calculated for delta H and delta S. All right, so delta H was 2,000, or sorry, keep getting my numbers mixed up here. So 2,802.5. Now this is in kilojoules per mole. So I think what I'm going to do is keep this in kilojoules and actually convert the entropy into kilojoules. So we'll just keep that the same. Oh, actually, this is just kilojoules. Ooh. It's getting to be the end of the quarter. My brain is starting to get really tired, as I'm sure you all can relate. Okay, so let's subtract the temperature. So we are given temperature in Celsius, but we want it in Kelvin so that our units with entropy will cancel. So let's just do a quick calculation. We're going to convert degrees Celsius to Kelvin. So we'll add 273. And that will give us 298. Okay. So now entropy we calculated as negative 259.2. Wait, let me double check. Yes. No, 0.5. All right, but let's convert this to kilojoules so that our units all match up. So I'm just going to multiply this by 10 to the negative 3, because remember, if we're going from joules to kilojoules, we have to divide by 1,000. Okay. So now we can multiply, add, subtract, whatever we need to do in our calculators. And our final value for Gibbs free energy will be 2,879 kilojoules. All right, so delta G is positive. Does that mean that this is a spontaneous reaction or a non-spontaneous reaction? So remember that for spontaneous processes, delta G is negative, but here it is positive. So that means we have a non-spontaneous reaction. Now, we probably could have also guessed that just from delta H and delta S. So delta H was positive, delta S was negative, and according to that table we saw previously where we look at all the different signs and then see what delta G would end up being, if we have a positive delta H and a negative delta S, that negative delta S actually becomes positive because it's multiplied by negative T. So the whole thing becomes positive, right? So that means that delta G is also positive. This is non-spontaneous. Okay. So photosynthesis is a non-spontaneous process. It does require energy in order to occur. And so, your plants out in your garden, they're constantly consuming energy in order to produce glucose and oxygen, and then we can breathe that oxygen in. All right, so the next problem is worksheet problem 9. So consider the reaction calcium carbonate is decomposing into calcium oxide and carbon dioxide. Okay, so we're going to estimate the Gibbs free energy for this reaction at each temperature. So down below, we've got 3 different temperatures. And then we're going to predict whether or not the reaction is spontaneous. And because we're considering different temperatures, we're going to assume that the standard enthalpy and standard entropy of the reaction do not change too much within the given temperature range. Remember, standard entropy and standard enthalpy are measured at 25 degrees Celsius. So if we're considering other temperatures, we do have to consider, are enthalpy and entropy going to change at those higher temperatures or lower temperatures? And here we're just going to assume that they stay relatively the same. Okay, so this will be pretty similar to our last problem. We're going to first calculate delta H and delta S, so we can plug that into our equation for delta G. And then we're just going to change the temperature within our equation to figure out how delta G changes with temperature. All right, so let's look up the delta H and delta S values for the reactants and the products. Okay, so we got delta H, and this actually doesn't have a delta there, so we got S. Oh, sorry, this is formation. And this will be in joules per mole Kelvin. Okay. All right, so now let's start with the products again, since that's what we'll be using first in our calculations. So we'll start with calcium oxide, which we're told is a solid. And the enthalpy of formation for calcium oxide is negative 634.9. And then the molar entropy value is 38.1. Now CO2 we already looked up for the previous problem. So we saw that its enthalpy of formation is negative 393.5, and its entropy is 213.8. And then our reactant is calcium carbonate, which is a solid, and its enthalpy value is negative 1207.6, and its entropy value is 91.7. Okay. So now we have everything we need to calculate delta H and delta S. So let's start with the first temperature value. Now delta H and delta S will be the same for each temperature, so we'll calculate those first, and then we'll just reuse them for parts B and C. Okay, so let's start with delta H. So the products, we have calcium oxide, and there's only 1 mole of that, and its enthalpy of formation is negative 634.9 kilojoules per mole. And then CO2, again, there's only 1 mole, and its value is negative 393.5 kilojoules per mole. And then we'll subtract the reactant. And again, there's only 1 mole of the reactant. And its enthalpy of formation is negative 1207.6. Okay, so when we add that all together, we should get a value of 179.2 kilojoules per mole. All right, so that's our delta H value. And is this reaction endothermic or exothermic? So this is endothermic. It's a positive delta H value, so it's absorbing heat. Okay, so now let's look at delta S. So we have 1 mole of calcium oxide again, and its entropy value is 38.1 joules per mole Kelvin. And we're adding 1 mole of carbon dioxide times its value of 213.8 joules per mole Kelvin. And then we'll subtract the reactant. And again, there's only 1 mole. And the reactant's entropy value is 91.7. All right, so when we plug all of this into our calculator, and again, you can always pause the video if you want to do some calculations and make sure you get the same thing. But we should get a value of, let's see, 160.2 joules per Kelvin. Okay. So now we're going to plug those values into delta G. So delta H we found was 179.2 kilojoules. Oh, and actually we don't need that mole there because we canceled moles. And then we're subtracting the temperature of 298 Kelvin times the entropy. Now I'm going to convert the entropy into kilojoules again because that will keep the units consistent. So we'll do 10 to the negative third joules per Kelvin. And when we calculate this out, we should get a delta G value of 131.5 kilojoules. Okay, so is this a spontaneous process at 298 Kelvin? No, delta G is positive. So now what's interesting though, okay, we said this was an endothermic reaction. Now the entropy of the reaction is positive. So is entropy increasing or decreasing? It's increasing, right? And that makes sense if we look at the reaction. We have 1 mole of reactant and 2 moles of products. So entropy should be increasing. There's more disorder with more moles of product. All right, so this really is a temperature dependent reaction. So whether it's spontaneous or non-spontaneous. Because the sign of delta H is positive and the sign of delta S is positive, so delta G really does depend on temperature. Now at 298 Kelvin, delta G is positive, so that would be non-spontaneous. So non-spontaneous at 298 Kelvin. All right, now let's do the same thing at a higher temperature. 1055 Kelvin. We'll see if this is spontaneous. Now, we're going to use the same values for delta H and delta S that we already calculated because we already said that we're going to assume they don't change within this temperature range. So this will be a little bit easier now because we've already done most of the work. So we said delta H was 179.2 kilojoules, and this time the temperature is 1055 Kelvin. And then we said that entropy was 160.2, but we're going to convert it to kilojoules. Okay, so when we do this calculation, we'll end up with a Gibbs free energy equal to 10.2 kilojoules. Okay, so is this process spontaneous at 1055 Kelvin? No, it's not spontaneous. Delta G is still positive. Okay, so now let's increase the temperature a little bit more to 1455 Kelvin. So let's see if this is spontaneous now. All right, so same thing as before. We're going to plug in the values we already calculated, but our temperature changes to 1455 Kelvin. And again, I'm just going to make sure my units match. Oh, whoa, skipped ahead a little bit there. I'll just erase that. Kelvin, there we go. Okay, so when we calculate this, we should end up with negative 53.9 kilojoules. Finally, we have a negative delta G value. So remember, if delta G is negative, that means we have a spontaneous process. So this is spontaneous at negative, or 1455 Kelvin. Now, remember, for this type of problem, you could also determine the temperature at which this reaction does become spontaneous. So to do that, we would just set delta G equal to 0 because that's the point at which it goes from negative to positive. And then we would rearrange the equation to solve for T. So the temperature at which delta G becomes negative, or the process becomes spontaneous, is equal to delta H of the reaction over delta S of the reaction. So it's just a ratio between those two. Okay, now we weren't asked to do that, but you could always do that separately if you wanted to. So I'm going to stop there. Again, this is just to help you go through questions 8 and 9 on the worksheet. Next time, we're going to talk about Gibbs free energy at non-standard conditions, because so far we've only been talking about standard conditions. So I will see you in the next video.